So let's go ahead and get started here. And again, the way that I'm going to do this is I'm going to put up the question, pause it, give you a couple minutes to work on it, and then we'll go over the answer together. Okay? So here's your first question. Will a galvanic cell based on the following reactions generate electricity? Explain how you know. Okay, so there's a couple of reactions there, and you want to decide. In other words, what are we asking here? If they're going to generate electricity, what are we really asking? Are they spontaneous? Okay. Alright, so go ahead and figure that out. Okay, so let's go ahead and talk about this one. Probably didn't take you too long to figure this out. Is the first one going to generate electricity? Okay, and really this is as simple as, so the answer here is yes. And this is really as simple as just looking at your reduction potential chart, right? So what we need to figure out here is the two half reactions we've got going on. The copper 2 plus 2 electrons is turning into copper solid, right? And then the tin solid is turning into tin 2 plus 2 electrons. So you can probably see now, this is the one that is copper. What's happening to the copper? Being reduced, okay? So this is reduction. So this must be oxidation, okay? If that's the case, then in order for this to actually occur, then the copper would have to have a higher reduction potential than the tin. And if you look on your chart, it does, okay? So the copper is higher up on that chart, so this one actually will occur. Alright, second one down here, again, if we're just using our half reaction method here, Ca2 plus 2 electrons is going to give us solid calcium. And then zinc, which is a solid to begin with, they're going to get oxidized into zinc 2 plus 2 electrons. Okay, so again, this would have to be the reduction, and this would have to be the oxidation. Is that going to occur? Okay, zinc is higher up on the reduction potential chart than the calcium. So for calcium to get reduced while zinc gets oxidized, that's not going to occur spontaneously. So the answer here is no, this will not generate electricity. Now, you could get this reaction to work by doing what? Passing electricity through it, right? Okay, so you could actually, if you give it energy, then you could get this to work. You could make it work in the reverse direction. But again, that's, you know, the definition of spontaneous is it works without ongoing outside intervention, okay? So this one, the second one, you could get it to work through electrolysis, but it would not produce electricity. It's not a good voltaic cell. Okay, next, when the following equation for redox is balanced and it's saying that it's taking place in an acidic solution, what will the coefficients be? Okay, I'll give you a couple minutes on this one. Okay, let's go ahead and talk about that one. So hopefully you remember your method for balancing using the half reactions. All right, so let's separate this into the two half reactions first. We've got Cr2O7 minus being changed into Cr3 plus. Okay, so that's one of the half reactions. The other one here, and again, hopefully you can see this at this point. If you can't, come talk to me, because I think I can walk you through it. Basically what we're doing when we're looking at the half reactions is everything that's not H plus or H2O, because we're going to add those in as we balance it. Okay? First thing we got to do, and some of you may have forgotten this, there are 2 chromiums on the left side, there's only 1 on the right side, so you've got to put a 2 here. That's going to mess up your charge if you forget to do that, okay? Next order of business, we need to balance our oxygens by putting 7 waters over on this side. Then we need to balance our hydrogens by putting 14 H pluses over here. Okay? Once I figure out my overall charge on this side, which is 12 plus, versus a 6 plus on this side, that tells me I need to put 6 electrons on this side. Okay? So that's our first half reaction. Second one down here, a little trickier maybe. There's 2 oxygens on the left, 3 on the right, so we need to add an H2O to this side. Okay? But now we've got 3 hydrogens on the left and none on the right, so we need to add 3 H pluses over here. Okay, and that gives our charge, there's 0 charge on this side, there's a 2 plus overall on this side, so we need to add 2 electrons to the more positive side here. Okay, Then, before we add these together, we need to make sure that the two equations are balanced in terms of the number of electrons. So we need to multiply the bottom one by 3. Okay, so when we write all this out, we got 14H plus Cr2O72 minus plus 3H2O plus 3HNO2 yields 2Cr3 plus 7H2O. I'm going to run out of room. Plus 3NO3 minus plus 9H plus. Okay, so then what I can do, I need to do some canceling on both sides. All right, 9H plus goes away, and we end up with a, I'm going to be very sloppy, but well, here, I've got an eraser. This is going to end up being a 5. Okay, did I do my math right? I think I did. And then 3 H2Os on this side, that's going to go away. Let's just erase these things. And we're going to end up with 4 H2Os on this side. Okay, and then everything should be balanced at that point. Okay. All right. Next, balance the following equation taking place in a basic solution. So now you get to practice one of those just in case. All right, so this one, same basic process, same process as before, except this time we're pretending we're in an acidic solution at first, and then we're going to fix it at the end. Okay, so CrOH3 going to CrO42 minus. Now this one's a little tricky as far as figuring out where everything goes. We've got 3 oxygens on the left side, 4 on the right. So we need to add 1 more water molecule to this side to balance our oxygens. Now we've got 5 hydrogens on the left side, so we need to put 5 H pluses over here. And again, H pluses are not in this solution, we're just pretending, and we're going to fix it at the end. Okay, so this is overall a 3 plus, and then there's no charge on this side, so we need 3 electrons over here to balance out the charges. The other one is the other half reaction, ClO3 minus yields Cl minus. Okay, add 3 H2Os to the right side to balance out our oxygens, and then we need to add 6 H pluses to this side. Now this one's a little tricky as far as the charge, because the overall charge on this side is a 5 plus, but there's a 1 minus on this side. So to get the charges balanced, each side needs to be a 1 minus charge. So we actually need to add 6 electrons to this side. Okay, which is nice, kind of works out so that we only have to multiply the top equation by 2, and then we're good. Alright, so long equation here, 2H2O plus 2CrOH3 plus 6H plus ClO3 minus yields 2CrO42 minus plus 10H plus Cl minus plus 3H2O. Okay, now we've got to cancel some stuff and then change a couple of things here. So the H pluses go away on the left side, and then we change this to a 4 coefficient on the right. There's 2 H2Os on the left, so those also go away. And this just gets changed to a 1 coefficient on the right. Okay, so what we're left with here is 4 H pluses on the right side. Okay, and that can't happen in a basic solution. So what we have to do is add OH minus to both sides of this equation to neutralize the H plus. And again, none of this is really happening. We're just pretending, and it's a good device to use to solve this equation. So I'm going to add, I don't have room here, so I'm going to add 4 OH minuses to each side, because that will neutralize the H plus on that side. But whatever I do to one side of the equation, I have to do to the other. Okay. So then when I do that, I'm going to end up with 4 OH minus plus 2 CrOH3 plus ClO3 minus yields 2 CrO42 minus plus, now we've added this 4H plus and this 4OH minus together to give us 4 H2Os, which we can then add to to the H2O that's already there, so now we have 5 H2O molecules plus Cl minus. Okay? No problem, right? It's a long process. It's rather tedious. That's what's going to kill you, is just how long it is. Okay? All right. So there's that. Everybody ready to go on? Next, how many electrons are transferred in the following balanced redox reaction? You might not even need 2 minutes for this one, so maybe I'll give you a minute or so, see if you can figure this out. Okay, so some of you would have been able to see this probably very, very quickly. Others of you, it might take a little bit more time, just depending on how good you are at doing this in your head. I think the easiest way to do these types of problems is just to figure out the oxidation number, okay, the oxidation state, and total it up. So on this side, you know, obviously the oxidation state on the gold is 3+, and there are 2 of them, so that's overall a 6+. The gold over on this side is solid, so it's going to have an oxidation number of 0, okay? This is a 6- going to a 0, okay? So in each case, it looks like 6 electrons are being transferred. 6 electrons are either being lost or gained in order for this reaction to occur. So the answer is 6. Now you could write out the half reactions if you want to, and then you'll eventually get to it. I think the oxidation state way is easier and faster, okay? Okay, next. 2 examples of species that would make good oxidizing agents, and 2 examples of species that would make good reducing agents. I'll give you a minute or so to think about that, and we'll talk about it. Okay. On this one, you're not going to have a question exactly like this on the test. The reason I asked this question is because I want you thinking about, I want you remembering what it means when something says oxidizing agent, because it's very easy to get that confused. Okay? So when I say a good oxidizing agent, that means that it is going to be what? It's going to be the one that's getting reduced. Okay, so something that's easily reduced makes a good oxidizing agent, and then, you know, vice versa. So a good reducing agent is something that is easily oxidized. Okay? So give me a couple examples, and all you have to do here really is just look at your chart, right? And you should be able to give me a couple of good examples of things that are easily reduced. Give me an example. Easily reduced, so a good oxidizing agent would be, okay, fluorine, F2 is a good one, right? That's the best one because it's the top of your chart. What else? Yeah, I wouldn't pick the cobalt necessarily, because that's cobalt 3+ going to cobalt 2+, right? So I would look for the next one where maybe it's actually going to a solid. Okay, so Au3+. You guys see that? Au3+, pretty good oxidizing agent, okay? Because it would much rather be Au solid, right? So it's going to have a strong tendency to get reduced if it's in that high oxidation state, okay? What about a couple of things that are good reducing agents, things that would have a tendency to get oxidized? Lithium. Now that's solid lithium, right? Okay. Lithium 1+ cannot get oxidized because that's its highest oxidation state. It couldn't lose any more electrons at that point. Or it could, but it doesn't typically do that, okay? So solid lithium would be a good reducing agent. What else? Yeah, potassium would be fine. I mean, the next one on the list, cesium, whichever one of those you want to use, okay? Solid potassium is also, I mean, really any of the alkali metals are going to be great reducing agents because they have such a strong tendency to be oxidized or lose electrons, okay? All right, next. Decide which of these half cells in this voltaic cell would be the cathode. Write the cathode half reaction that will occur here. Okay, I'll give you a minute on this one. Okay, so let's go ahead and talk about this one. I said okay really loud that time. It was a loud okay. So what I didn't say before that I just kind of assumed on this one. Typically this is the way these voltaic cells are set up, where you have the ion in solution around the So the electrode. So the copper is going to have copper 2 plus in its solution, and then the silver electrode would have silver 1 plus. So then we want to decide which one is going to be the cathode here and write the cathode half reaction. So between those two, which one is going to be, well, first of all, cathode means what? Reduction, red cat, right? Okay, so which one is going to have the higher tendency to be reduced here? Okay, it looks like the solid, the silver, solid. The silver 1 plus is going to have a higher tendency to be reduced, okay? So the reduction that's going to occur here, so this is our cathode, right? And the reduction half reaction would be Ag plus an electron yields Ag solid, okay? So what we're going to observe here is we're going to see this Ag plus, as it gains electrons, the silver electrode should start to get bigger, okay? Alright, that's as far as we're going to get for now. So again, this video will be finished in maybe next hour and then in 5th hour as well, okay?